Start by understanding what a PLC, or programmable logic controller, really is. Imagine a computer specifically designed to control equipment in industrial settings, everything from conveyor belts to food processing machines and auto assembly lines. PLCs are the backbone of modern automation, replacing old hardwired systems with flexible, programmable solutions. Like microcontrollers or PCs, PLCs thrive in harsh environments, handling dust, humidity, and electrical noise with ease. Their architecture is robust, and they're programmed using intuitive languages like ladder logic. With PLCs, industries gain flexibility, rapid changeover, and reduced downtime, making them essential for boosting productivity and quality. As we move forward, we'll explore the basic parts of a PLC and how they work together to automate complex processes. Now let's dive into the core components of a PLC. At the heart is the CPU, acting as the system's brain, reading input data, executing user programs, and sending commands to control devices. The programming device, often a PC with specialized software, allows engineers to create, edit, and troubleshoot programs. Input and output modules connect the PLC to sensors, switches, motors, and other devices, forming the bridge between the digital world and physical equipment. The power supply module ensures everything runs smoothly, powering both the CPU and connected devices. These modules work together seamlessly, enabling the PLC to process inputs, execute logic, and control outputs in a continuous cycle. This cycle is known as PLC scanning, which involves checking input status, executing the program, and updating output status, repeating endlessly until the system is switched off. For PLCs, industrial automation relied heavily on hardwired panels filled with electromechanical relays. Electricians had to install miles of wiring, and even minor changes required extensive rewiring. This approach was costly, inflexible, and time-consuming. PLCs revolutionized automation by eliminating most hardwiring. Now, changes are made simply by updating the program. Industries quickly adopted PLCs for their flexibility, space efficiency, and cost-effectiveness. Troubleshooting became easier, as visual operation could be observed on screens. PLCs withstand severe conditions and offer pre-programmed functions like logic, timing, and counting. However, they do have limitations, such as closed architectures and proprietary parts. Despite these, PLCs remain the preferred choice for industrial control, offering unmatched adaptability and reliability. Programming a PLC is done using ladder logic, a symbolic language that resembles a ladder with vertical rails and horizontal rungs. Each rung represents a control circuit, using contacts and coils to determine when outputs should be turned on or off. Ladder logic is intuitive, allowing engineers to build complex control sequences with timers, counters, and logic functions like AND, OR, NOT, NAND, and NOR. For example, a timer can control a device for a specific duration, while counters track the number of events. Latching circuits keep outputs energized even after the input is released, and interlocks ensure that incompatible actions don't occur simultaneously. These programming techniques make PLCs incredibly versatile, enabling precise control of everything from motors to water-level systems. As we wrap up, remember that PLCs are the foundation of modern industrial automation, offering reliability, flexibility, and ease of use. See a practical example of PLC in action with a water-level control system. Imagine a tank with sensors and a solenoid valve, all managed by a PLC. The ladder program starts the system, monitors water levels, and opens or closes the valve as needed. When the water drops below a certain sensor, the valve opens to refill the tank. As the water rises and reaches the upper sensor, the valve closes, stopping the refill. The cycle repeats automatically, ensuring efficient water management. The PLC's internal relays and interlocks make the process reliable and responsive. If the stop button is pressed, the system shuts down instantly. Such applications highlight the power and precision of PLCs in real-world automation, making them indispensable for industries seeking smart, efficient control solutions.